Hello, everybody. In this video, we will train a small neural network that will predict the solubilities, and we will be using the DeepChem packages. If you haven't already, I would highly recommend visiting the DeepChem webpage and check their documentations. And my favorite part is the MolNet portion of this one, where you have a lot of the data sets already pre-built into it so that they can be easily loaded into DeepChem and you can mess around with them and have fun with it. So let's try to do this. I'll be obviously posting this page, this Jupyter notebook in my GitHub page, but I'm using a book called Deep Learning from Life Sciences for Life Science, and I'll have the link for that book. I would highly also recommend following that book. It's a good book to apply deep learning for a lot of biological problems. Okay, so let's start. So let's import DeepChem as DC. I'm using Jupyter Notebook. You can use Google Colab as well, but just make sure you pip install DeepChem into Colab. Because last I used, it was like last year, the DeepChem was not pre-built into Google Colab so that you cannot import. So you have to install before using it. So right now I have installed DeepChem on my computer. Just ignore this missing dependency because this Conda environment, the one I'm working on right now, doesn't have PyTorch or JAX. And it's going to be perfectly fine. So let's load our data sets. So let's call task data sets and transformers as dc dot molnet dot so we can do all sorts of these data and load them directly into our page. So let's do load Delaney data sets. So featurizers. So again, this is the important one. So how would you like to featurize each of your molecule? So we want the graph convolution featurizers. So let's do it. So let me explain this Delaney data sets in a second. So if we go back here, so let's go over the Delaney data sets. Oh, it's right here. So this is the data sets with about thousands molecules and where the solubility was written as if moles per liter. I'm not sure how much chemistry background you have, but solubilities is important in drug discovery because you want your drugs to be absorbed into your body and hence it has to be properly in the proper solubility range. Okay. So that's why scientists who design drugs, they try to optimize the solubilities to the perfection so that it can be easily absorbed. So this data set has solubilities in moles per liter on the logarithm scales. And you can go have a deep dive into the data sets. If you want to, feel free to check out this paper. Okay, so let's split our data sets into train, valid, and test data sets equals to data sets. So now we have split it into it. You can check their shape. So let's do print train.x.shape. So you notice is that it has 902 molecules. Each training data sets has 3 categories. One is X variable, of course, the molecules after featurations. Next one is Y variable. So you can see it has the second column that shows us the solubilities. And then also it has the W variables, the weight variables as well. And if we go do the same thing for our test, you will notice it has 113 molecule in our test data sets. Okay, so let's try to build our model. So we're gonna be using dc.models and we will be using, let's see, dc.models conmol GraphCon model. And then let's look at what's in here. So you want to use the so this GraphCon model uses the featureations, the GraphCon featureations. So we want to make sure that they matches whichever model you pick. Make sure your data set is featureized to that. Uh, so let's look at here what are the things we need. We need tasks. We got one task which is just basically solubilities of each molecules, and we want the regression mode, and this is important because we want our model to predict a value, a continuous value, which should be as close to its actual values. It's not a classification problem, so it's more of a regression problem. So the default mode is classifications. So you can see the mode default is classification. We have to change it. One important thing is GraphCon layers, how many layers we want. So in this case, this model by default is 6464. I have messed around with a bunch of different values with different dropout rate to maximize the testing data sets. Obviously, the training data set will overfit, but your goal is to do good on the testing data sets. So I've noticed high dropout rate is good, but I want to make this layer, make this basic layer as fast as possible, and so that it can, so that we can finish this in a videos. Okay, so again, let's go over GraphCon layers. We will just use the default 6464. I've seen 3264, 3264 with 50% dropout rate, 0.5. Okay, let's see if we miss any important stuff. Yeah, it seems pretty good. So let's hit model and let's try to fit our X data set, training data set. So model.fit, and we'll be using on our training data sets a number of epochs. So number of epochs means how many times you're passing your entire set of data. So let's pass our entire data set 100 times. I did with the higher dropout rate. You want a 50. Right now dropout rate is 50, but let's do it 20% actually, so it will be faster. Not faster. It will not be as good. With 50% dropout, I had to do anything above 500 number of epochs did decently. I think this one would be okay. So let's try to do this 100 epochs. So it will output a average loss. See how good that loss is. So let's try to evaluate our model. So model.evaluate. But before we evaluate, so how would we evaluate? We will evaluate by using a matrix, right? So let's create a matrix. dc.matrix. So it has a metric class. So DeepChem has metric class. Okay, so we got 0.2. Okay, it wasn't as good as I was expecting. The loss is 0.2. It's gonna be terrible. Maybe let's just increase to 128 and try again. Okay, so what I was saying. Yep. So we got metric. So the DeepChem has a wrapper class called metric, where that would operate really well with the built-in DeepChem model, the one that we are using right now. So you just have to use this wrapper class, and you can call some of the common metric scales. So in this case, we're going to be using Pearson's R2 square. dc.metrics.pearson R2 score. And let's evaluate our model. So train scores. Oh, I forgot to hit the epochs. Dang it. Okay, so let's model. So we are refitting it. So let's do our training score. As the model is training, let's just write our code so that we can move forward. So let's go with our training score. It's gonna be model.evaluate. So we're gonna be evaluating our model. and we're going to be evaluating on our training data sets, and then we will be using metrics to evaluate. And it has a transformers, which is basically the transformers is the same one we loaded it, so we have to assign which transformer it is. So that's our training score. Let's print our train score as well. So while we are waiting, let's just write the code for the test score as well. Okay, so we got a better average loss this time, 0.07. Okay, so I just want to make sure we don't have any typos here. Okay, Pearson R2 score, there was no typo in there. I always misspell, forget something. Okay, model.evaluate seems reasonable. So test score is gonna be model.evaluate. And we're gonna be using our testing data sets, and we'll have our metrics, and also we'll have our transformers. And let's print our test score as well. Okay, so oh, I knew there was a typo. Transformers. What did I do? Metrics transformer. Did I do a typo here? Oh, I did a typo here. Okay, so dang it. Okay, so we have to use the transformers here. So okay, so okay, so please ignore this one. So when I will post this actual this on the GitHub page, I will make this typo error. Okay, so you can see here, this model has given us 94% on our training score, and testing score is 72%. So it's did pretty good. It's definitely overfitting 94 and 72, but not comparison to 94, 72, and with just basic modifications, we did fantastic, I would say. We can mess around with it, and if you increase the dropout rate, this number would go up so that it won't overfit as much as. Okay, so we got our testing and training score, but how can we implement this? Well, let's say you are designing drug, and you created a couple of molecules. How would you use your molecule to test what is the solubility would be by using this model? So let's draw a couple of molecules here. So this is a smile generator. So smile generator is basically converting a structure into smile notations. And the smile is going to be read by RDKit packages, and it will convert into a machine readable code. So I know I draw this molecule, and I'm not sure how much chemistry background you have, but when you have oxygens or nitrogens and many of these present in your molecule, it's going to interact well with water and makes it more soluble because they can form hydrogen bond with each others. So I know that this will have higher solubilities because based on the functional group. So let's copy this, and let's create a list. Smile list is going to be this. And let's create another molecule, which I know that it's not going to have as big of a solubility. So this is a cyclohexane derivative right here. It's all carbon atoms. When you don't have any polar group, dang it, I deleted. So when you don't have any polar atoms, it tend to be not soluble. And I know that this should have poor solubilities. Let's see if our model is predicting that. So you can mess around with this smile generator and draw a bunch of molecules and see where you're going. And I'll leave the link to this online page so that you don't have to download crazy softwares, expensive softwares. You can just draw a molecule, get the smiles, and move on. Okay, so these are two smiles. smiles list. You can do as many as you want. So first thing that we have to do is we gotta import RDKit. So RDKit is a package that's used for reading and messing around with molecules, and that's used for everywhere, right? I should do a tutorial on RDKit. Let me know if you want a tutorial. I'd be happy to create one. So import RDKit. Okay, so we need the from RDKit we need kit import chem. We need the chem modules. Okay, so first thing that we have to do is convert this smile into a mole object, and that mole object would be able to readable by the DeepChem module, DeepChem package. So let's create a mole object. Again, to create the mole object, we have to convert this list into another list. So chem.mole from smile. So we need mole from smiles. And for molecules in this smile list. So let me read the code again. So for molecules in smiles list, so in this list, for every molecule, what we want to do is we will take another list and we'll convert each of the smile into a mole object. And then once you're done, you can test it out. So you can see we created a 2 mole object in this list. Okay. So next thing we want to do is take this mole object we created using RDKit and featureize it. And this featureization is going to be the same featureizations where it's going to take the molecule and convert into the same featureizations on which we trained our model, right? So this model is using a specific type of featureizations molecules. Okay, so let's do it. So let's call it featureizer is dc.feat .conv mole featureizers, and we're gonna featureizing this. So let's create an array. Let's call featureized molecule is gonna be featureizer. Not that one. Featureizer dot featureize. The featureize functions would be able to take this featureizer and we'll be able to featureize. And then we are featureizing our mole object. So let's put it here, mole. Okay, so we have featureized our molecules. Now this is what our model will be able to read. So now we can use our model, the GraphCon model, and use this to predict the solubility. So let's say prediction. So we're going to be predict. It's going to put out values. So predictions is going to be model dot predict on batches because we have multiple molecules. And then we're going to be passing our batch, which is the featureized mole. This is a batch. And let's print our predictions. And you can see we got a number very high, another one is negative. And just like I said earlier, the first molecule has a bunch of nitrogen and oxygens, so it should have higher solubilities. And as expected, our model did okay. Well, I'm not sure what is the exact number, but it gave a high number. So it tells us that this molecule is highly soluble in water. However, the second one, which is just the carbon chain, and usually when you have just the carbon chain, they are highly insoluble, and it gives us a very negative number. So this is providing an absolute values. So that's what the model did. It wasn't a classification problem, it was a regression problem. Again, this number may or may not be exact because based on our score, it's 72% close, right? So closer to 1 is good. Okay, so that's how this a out of the box model that we built using DeepChem to predict the solubilities. Again, I will make this correction here of the typo. Sorry about that. And when I will post this in my GitHub page. All right. So please stay tuned for more videos from all this. I have so many more videos from datasets. I will show you. Try to do post more videos on some of these datasets. See how many I can do it. All right. That's all for today. Thank you.